Welcome back. This is the last of the reaction that I want to go through with you all before moving on to a newer content. Now, in sharp contrast to the first three reactions, this one is a nucleophilic reaction. That means we are going to generate a nucleophile in the process of our reaction, right? Now, what I have done here is, prior to starting the video, is rewrote this molecule containing a triple bond in this form. So you see that a carbon can only have 4 bonds. So this carbon on the triple bond does not have any more hydrogens, whereas this one can have one more bond, which leads us to believe that there is a hydrogen here, right? Good. Now, all I have done here is just redraw this molecule in a different way so you can see what we are trying to do. All right, and then you got your NaNH2. Now, where does this reaction find its application is, say, this is really to generate your nucleophile, this whole thing, okay? This whole component is to generate a nucleophile. Now, what you will see in class is I could easily manipulate it into a multiple problems, and one of them is, depending on the substrate, which is this, your product would be different, and you can actually set your requirement on what you want. Currently, this is actually my reactant where I'm starting with 2 carbons, right? Say I want my product to contain more carbons. Whenever you had to add, you're starting with 2 carbons, but you want to end with more carbons, then this is the method you choose. Say I want 6 carbons in my long chain. Keep in mind, I'm not talking about just the total number of carbons. I want 6 carbon in my longest chain possible. Here I'm starting with 2. So you must start with 4 carbons. Now you could have done it without the extra branched carbon, but that's not what we're so worried about. Okay, this contains 4 carbons in the straight chain. That's what we're really interested in. So whenever you want to add more carbons, this is the reaction you sought out to. Okay. Now keep in mind, from your general chemistry, your NaNH2 is nothing but, this is plus, sodium is always plus, it's a metal, and your NH2 is your negative, right? Now, your sodium is merely a spectator ion, and this makes it a strong base, okay? And your NH2 minus is really what we're interested in, and that's what's going to react with your hydrogen on this compound containing a triple bond. And I want to add one more piece of information. Your single bond is less strong compared to a double bond, which is less strong than a triple bond. So this is your strongest, and this is your weakest. Okay. Why is that knowledge important? Because the hydrogen attached to a carbon containing a triple bond is more acidic than a hydrogen attached to a carbon containing a single bond. So, we also have a hydrogen here, but this hydrogen is attached to a carbon through a single bond, whereas this hydrogen is attached to this carbon, which is attached to a triple bond, right? So this is also carbon right here, okay? That's attached to hydrogen, but it's single bond. Here it's triple bond. So this is more acidic. And what is the base like? Obviously, a more acidic hydrogen, right? So what happens now here is your NH2 minus, which is your base, abstracts this hydrogen because that's essentially what it wants to do. And in the process, the bond comes back to the carbon. Now, if you remember from any reaction I have told you, whenever a bond comes back, it brings a negative charge. Whenever a bond goes out of a molecule, it leaves a trail of a positive charge, right? So I'm going to redraw this in a different color just for visual purpose. So what happens here is, this is what has happened. Plus, obviously, you have NH3. Now, this is your nucleophile. All we have done here is, the starting material is just a nucleophile. So this is a nucleophile. Now, this is not the actual reactant. This right here is the actual reactant. So this reacts with CH3, CH2, Br, right? Now, This is a strong nucleophile. It's going to react with the primary alkyl halide, so it's basically substitution. So this reacts with this, so SN2 mechanism, and then this comes out. I'm going to write SN2 here. So what is the product? Well, I'm going to write it this way so you can see it. Okay, this C attaches itself to this C, and then that's the Br come out. You cannot just attach it to any C as you wish. It can only attach itself to the carbon that contains the leaving group. And then the remaining looks as it is. Now you see, we have got our 6 carbon requirement in the longest chain, 4, 5, and 6. And this is a branch. You could have done it without it or with it, it doesn't matter. This is a specific type of product. So now we have 6 carbon, and this is actually where the reaction ends. Okay, this is a product. Okay, basically you have connected this CH3CH2 with this whole thing. It's like this is all the coaches and this is the engine, and the CH2 part of it is actually the rear end of the engine, which is where you're connecting the whole molecule. So if you just want to keep adding carbons to your starting reactant, this is the reaction you choose. But here's a real testament of your Chem 330 knowledge. Let's see if you can come up with the product. Of course, I'm going to show you the product, but I highly recommend you pause the video when I tell you to and see if you can come up with the product. Let's say the product we made here reacts with hydrogen, palladium, and carbon, and then also with Lindlar catalyst. Remember? What do you think is a product when this is one condition, this is the other condition? What do you think is happening here? All right, well, let's do something. Let's go ahead and write the template first. Okay. This is one. And I'm going to write this in another color so that, you know, I can show you the difference. So right, in both the cases hydrogen is added, but when it is hydrogen and palladium, the triple bond is completely gone. You cannot go to a double bond stage, right? So what happens here is this carbon has 2 bonds, right? So it can have 2 more hydrogens. So when you add a hydrogen to a triple bond, basically both the double bond is gone. So for every double bond removed, you add 2 sets of hydrogens, or a set of hydrogens. So you will have 2 sets added for each of the double bond removed, right? This is a complete, this process doesn't stop. If you want to go from a triple bond all the way to a single bond, which is this, then you add a hydrogen and palladium catalyst. If you want to go from a triple bond and stop at a double bond, then you add a Lindlar catalyst. Means you end with the double bond, right? Let me actually, I think I messed it up by overdrawing it. So if you don't want to go all the way, you only want to end with the double bond, then you use a Lindlar catalyst, which in that case, I'm going to add now a different color just to see if this makes sense. We have removed only 1 bond, so we only had 1 set of hydrogens. Remember, it's very important. See how the content is related. You know, everything in chemistry is so related that you have to understand the process. Without understanding the process, trying to memorize a large sum of information would never help you, and that's probably one of the reasons also you might struggle in a chemistry classes. You're not really fully understanding it. You are partially remembering something, and trying to relate that into a new context is not going to help you. So chemistry is not about memorization, it's about actually understanding the material, because I don't know how much you will remember. Like I said, this information we learned in 330. So if you think you're going to memorize and forget 330 material, you would never be able to answer this question in 335. Whereas if you've understood that hydrogen and palladium is used if you want to completely get rid of a triple bond to a single bond, and the Lindlar catalyst is is to take you from triple to double. If you remember that more conceptually, you're going to probably answer it correctly here. Anyways, that is something, since I have brought it up, it's fair that I might test you on that. So it's important that you remember it. And then we're going to try multitude of different ways of asking you this question. So it's important that you try to understand what has happened in the 4 videos that I've posted on this topic. So after this video, we're officially done with the um, electrophilic and nucleophilic reaction. We are going to learn something which is different. Earlier, we learned it from a purely aromatic perspective. Here, we are going to learn addition reactions of nucleophile from not only aromatic but other perspectives. All right, so stay tuned for the newer content.